Okay, so I mean, before we get started, just a quick reminder. So I'm going to post the homework to part two, like sometime tomorrow. And then the whole homework two will be due next Friday. Okay, so yeah, so basically what we're going to do today is to pretty much finish up the last part of the chapter two, which is actually partition of unity. So as I said, that the partition of unity is actually a tool for us to patch local things, right? So like remember we have a like a lemma or proposition earlier or corollary, I forgot, I think it's 2.8, which basically says if you have uh, like locally, if you have like each small open set, right? And for each open set, you have a corresponding, like say smooth function, but only for smaller open set, right? And if those smooth maps are uh, like equal on the overlapping region, then you can patch those smooth manifold together to get a global maps, right? So you patch the local smooth maps to a global one. But you can see that in order to use the corollary 2.8, the criterion is first the domain for each smaller local smooth map has to be open. Okay, so that's one thing, right? Because we actually, if you go back to read the lecture notes for Tuesday, what we actually found a counter example where if the domain can be possibly closed, then even though two maps agree on the boundary, then once you glue kind of patch together, it may not be close. It may not be like smooth map anymore, a global one, right? So we raised this question that, okay, if we have some kind of local closed smooth map defined on a closed subset, what should we do, right? How do we kind of either patch together or maybe extend it to a global smooth map? So this requires the use of partition of unity. So I think at the end of Tuesday, we actually introduced the definition of partition of unity, but that's just review so we can proceed here. So partition of unity, it's kind of also you can tell from the name that it's a partition of unity. Unity means one in some sense, right? Then partition means you're going to have a whole bunch of like functions, and at each point, it's going to add up to one. So you essentially cut one into several pieces, right? That's essentially what it means in some sense. So basically, you give me an open cover, right? It doesn't necessarily need to be countable or uncountable, just some open cover, right? Whatever you give me an open cover for a smooth manifold, how do we define a partition of unity subordinate to this open cover? That means you're going to have a family of continuous function with the same index, meaning for each open set X alpha in this cover, you're going to have a corresponding function per psi alpha. Okay, so you're going to have a family, and then the index will be the same, right? And this indexed family of continuous function, it's going to be globally defined, right, from the whole manifold to R, right? And it's going to satisfy the following like four criterion. First, it's going to be non-negative, and even more, it's the value, right? It's going to be between 0 and 1 for any alpha in this family, and also any points, okay? And the support of this function, each function is going to lies in each corresponding open set, right? So support means the closure of the points where the function is non-zero, right? So it looks like so let's say if you have a X alpha, right, for example, and if you want the support to be in it, and then also the function is from between 0 and 1. So roughly speaking, it might look like the way we construct it later on is like you have some kind of bump here, right? And then it's 0 outside X alpha because the support actually is contained in this open set S alpha, right? And then you can imagine that the highest you're going to get, the height is going to be 1. And then elsewhere is in between, right? And the family, and on top of that, even more, we want to define this family nice in the sense that like the family of support right? This set, so each support, like support of each function is a set, right? It's a closed set. And all this support, right, if you view it as a collection of sets, it's actually locally finite, right? So basically it means that, okay, you might have like a whole bunch of X alpha to get like nearby, right? So let's say this is X alpha, X beta, and X gamma, right? And you definitely will have the corresponding, I don't know, like some like function per psi alpha, per psi beta, per psi gamma. But you cannot have too many non-zero term in the sense that, for example, if you pick a point, say P, right? You can find the open neighborhood, right? Such that this open neighborhood is going to only intersect the non-zero part of the function. You're going to only intersect finitely many non-zero part, right? So that's why essentially this is what I said here. For each point X, right? If you call it X, you can find a neighborhood such that it's going to only intersect finitely many support. That means even though, okay, we want the function to be between 0 and 1 for each open set, but locally around each point, you don't want to have too many those functions, which means that only finitely many function nearby the point has non-zero term, right? So every function else, everything else should be 0, okay? And the reason we require 3 is that later on, when it comes to the fourth criterion, when we have such summation of the family of function per psi alpha, we don't want to have to deal with infinite many sum, right? Because when you consider adding like infinite many like sum of the function, it will like you will have the problem with whether it's convergent or not, right? Like if you, I mean, you took advanced calc before, if you're dealing with like infinite many like things adding together, summation of infinite many function, you always need to worry about, oh, at this point, is it convergence, right? All these like problematic things. So first of in order to be partition of unity, the whole point is that for each point, right? At each point, if you add up those value of the function at this point, it's going to be add up to 1. But because of the criterion 3, we know that at each point you can find a neighborhood such that it only intersects finitely many support. That means you're going to have this sum will only have finitely many non-zero terms. Okay, so there will be maybe like infinite many other terms that are 0, right? For example, you might have, I don't know, from, I'm just making up, from like per psi, I don't know, like 5 to per psi infinity, right? They're all 0 at one point, but only finitely many of them are like non-zero, okay, between 0 and 1. Okay, so when you add up those things, then it's going to be a finite sum anyway, even though you might have infinite many family of functions, but around each point, you're going to see only finitely many non-zero terms. That's the beauty of the partition of unity. So the question is, how are we going to build up such nice family of function, right? So-called the partition of unity. Or actually, the question we should ask is, does there always exist such partition of unity, right? So keep in mind that in the definition of partition of unity, we only require the function to be continuous, but we actually want a little bit more. We want something stronger to work with. So actually, you're going to see in a minute that for smooth manifold, we can always find a smooth partition of unity. Okay, so and then this is actually related to the property that a manifold is paracompact. Okay, but before we really proceed to the theorem, let me show you like both theorem and the lemma. So in order to prove this existence of smooth partition of unity, I need to recall this lemma. I don't think I mentioned it back in the chapter 1 because back then we don't need it. So now I'm going to mention it. And I mean, you can try to prove it, but it's actually not hard to imagine, like it's quite intuitive. So the lemma 1.13 basically says, if you already have a family of sets, right, that's called it a script X, and it's a collection of subsets in the topological space, And that's assume if this collection is already locally finite, okay, right? Then if you take the closure of each subset in this collection, then if you take the closure, right, X alpha bar, while X alpha is from this collection, then the new collection, right, you collect all this like closure of all the sets, this new collection will also be locally finite, right? This is actually not hard to imagine, right? So if you already have a locally finite, right, set, right, and then it might be open, right, or might be closed, right? So you already have some open set like this, and then then it's already locally finite, meaning at each point you can find a neighborhood such that it only intersects finite many of them, right? So you can imagine now instead of the original set, if you take the closure of all this set, right, meaning you include all the boundary, right? So if you like take the closure of them, you can imagine you're not going to suddenly intersect infinite many of them, right? Because you just add a little bit, right? So this is actually not too bad to imagine. And the other things we're going to also use later on is that if you consider the union of those set from the collection, then you take the closure of the union, right? It's going to equal to the union of the closure of those sets. Okay. And in order to prove that, you just have to prove like both direction, right? One side is included in the other, and then vice versa. Okay, so we're going to use this lemma 1.13 later on when we prove the partition of unity. And for theorem 2.23, basically it tells us that if you have a smooth manifold, either with or without boundary, okay, doesn't matter. And also you have a collection of open cover, right? This has to be an open set and also open cover, which means that you can cover everything, like you can union everything or some of the things such that it's going to be the whole manifold. Then it just says that there exists a smooth partition of unity subordinate to any open cover you give me, right? So the open cover you give me might be bad in the sense that there's uncountable many of them, right? But still, you could actually find a partition of unity such that, like, if you go back to the definition, right, such that the support of the functions is actually locally finite, right? And you can create a whole bunch of family of functions such that it's between 0 and 1, and also the support will lies in the open cover that you give, open set, right, in the covering that you give me, right? And on top of that, this is the whole point why they call the partition of unity, means each point the function is going to add up to 1. The family of functions is going to add up to 1. So how are we going to construct? So this is like definitely like a construction type of thing. So as I mentioned on Tuesday, that the proof is quite involved in the sense that there's a lot of detail. So to be honest, that even though I really want to present the proof so you can see it all at once, but I really don't expect that if you haven't read the proof before, if you just watch me doing it, it's actually very hard to right away understand it. So because it's very involved and there's a lot of detail you need to think about that, why this is the case and why they do that. So so my goal here is just to give you a rough idea about how to do this kind of construction, right? And then later, and then you're going to see the construction we're going to use. The function looks like a bump function. We're going to use the bump function we actually defined earlier, right? Remember, we used to have this function where in the open ball, it's actually constant 1, and it actually decreased to 0, right? It's 0 outside another slightly bigger ball, right? So those type of bump function, or we're going to take advantage of it. So it's like kind of like you patch up things, okay? So okay, so let's see how are we going to prove this. So the proof might actually a little bit long, so you want to be a little bit patient here. So first, I'm going to just prove the version for only manifold without boundary, because for boundary, then you need to really take care of boundary point. That's a little bit more work. So we stick with just a simpler proof for manifold without boundary. So basically, first of all, since we have each open set, right? You have an open cover and each set is open, right? And you can actually show that, I mean, we talked about this before. If you have an open subset of a smooth manifold, then this open subset is a smooth manifold itself, right? So basically, this set X alpha is going to be a smooth manifold, or you can say smooth submanifold, right? Then if it's a smooth manifold, then the first thing that we have is that this is actually where all the like topology property we discussed before comes in. Then by proposition 1.19, I'm going to tell you what that is, but let me just write it down. Then we can actually find a basis that's coded B alpha, because one basis corresponding to one open set, right? So we are going to basis consist of regular coordinate ball for O alpha. So what is the statement of proposition 1.19? It means that you can always found for any smooth manifold, you can always have a countable basis consisting of regular coordinate ball, right? So coordinate ball just means that all the open set you found in the basis, actually it's going to map to open ball in Rn, right? Regular just means that those ball actually are, you can actually those ball are, you can find another open ball such that the closure of the original ball lies completely in a bigger ball. Okay, I'm going to write down more later on. So basically, this is the first thing we use, right, for from the topology in chapter 1. So we can, for each smooth manifold, we can do that. So this means for each open set X alpha, I have a corresponding basis. Okay. And if I have a basis for each local things, then if you union all of if you have a basis for each open set and you take a union of it, right? And essentially it's going to be another basis. So actually, this is actually a basis of regular, and I actually want to be precise that this is a countable basis, right? Okay, then you can actually, I don't want to put it here, otherwise, okay. So I want to take the union of all this basis, right? So for each open set, you have one corresponding basis, and you take a union of it, and you can imagine this new collection, whatever, right? It's going to be a basis for the whole manifold, right? Because you already have basis for each smaller open set. Then of course, if you take it all together, then it's going to be the basis for the whole thing. So this B is going to be a basis for the topology of M. Okay. Now the thing is that, okay, this is a basis that we can choose, right? For each topology, you can always find different type of basis, right? As long as it satisfies the definition of being a basis, right? We might have different type, right? I mean, you can imagine in linear algebra, if you have a vector space, you can always pick a different basis, right? Basis is not unique. So this is one particular basis for our topology. And now we also need to use another topology result. So by theorem 1.15, right? Essentially, I called it paracompat property. Right? Basically, this means that if you give me a open cover, right? And then you give me a basis, right? What's essentially it tells you that every smooth manifold is paracompat. What's paracompat? Meaning every open cover has a locally finite refinement, right? So basically, and then even more, this theorem 1.15 actually proves a little bit more. Not only it proves the manifold is paracompat, it actually proves that like the countable locally finite refinement of your open cover actually can come from the basis you choose. Okay, so let me just write down what I said, or I mean, if you have the textbook with you, you might want to just read the statement. That's probably faster. So then essentially by this theorem, our open cover that we choose at the beginning, so the open cover X actually has a countable locally finite refinement. And this refinement actually, the set actually comes from those from the basis. This is essentially what theorem 1.15 did, right? It's actually a little bit stronger than just being paracompact. It actually says that this countable locally finite refinement actually the refinement can be obtained from the elements, the open set in the basis. Okay, so now we have this set up, and now I want to use those like locally finite, like this property. So I'm going to need the what's it called, the lemma 1.13. And to be precise, actually the statement A. Remember the statement A says if you have a collection of locally finite sets, right? This collection is locally finite and you have a bunch of sets. Then if you take the closure of those sets, this new collection of the closures is also locally finite. So basically, if you take the closure of all this, if you take the closure of all this BI, this refinement that we just obtained, right? And you take the collection, then this new collection, this new cover is going to be locally finite. Right, this is from what we just saw. Okay. So first, then it's actually good. As you can see, now we obtain something that's locally finite, right? Then this is going to help us to build the partition of unity, right? Remember, the partition of unity tells us that later on we want to make sure that the support, the family of support, the collection of all the support is locally finite. So this basically kind of tells you that you need, at some point in the proof, you need to create some locally finite subset, right, or collection. Otherwise, you cannot create those nice property. So now another thing we want to use is the regular property, right? So we actually have the regular coordinate ball here. We need to take advantage of that. So since each BI, right, those coordinate like a regular coordinate ball. So since each BI is a regular coordinate ball in some X alpha, right? Because it's a refinement, right? So it's going to contain in some set in from the open cover, right? Because BI essentially is a refinement, meaning it's going to be smaller or in some sense contained in the original open cover, right? Then it's regular, right? So regular means you can find another coordinate ball, a little bit larger. Actually, let me code it. I want to use the different, let's call it prime. I want to use some notation, but at the same time, want to be consistent with the textbook. Okay, so let's stick with the same notation. So being regular means you can find a slightly larger coordinate ball, and the closure of the original ball is included in this larger ball, open ball, right? And you're going to have a smooth chart, right? Smooth coordinate map, which is essentially the phi, right? And which is going to send the closure of this original ball to some closure of a ball in Rn, right? And even more that the homeomorphism here is going to set the larger coordinate ball to, because it's already called coordinate ball, right? So it's going to send to a ball in Rn. But this ball should be larger. So essentially I have the radius Ri prime is bigger than Ri, right? So that's just the setup. That's essentially definition of regular coordinate ball, right? I just kind of rewrite the whole definition, and you can actually check the definition. It's really just the definition of regular ball. Okay. So now the thing is that because why we need regular ball? Because remember, we want to build something that the support is completely contained in some set, right? So this essentially guarantees that, okay, you have this ball is actually strictly, in some sense, even including the closure, is strictly contained in something slightly larger. So that will help us when we're trying to build a bump function, right? So you have some leeway to let the function going down to 0, right? While keeping everything inside 1, right? That's the whole point, okay? So that's why we need the regular property here. Okay, so I just want to give you a heads up. All these things I write here is really kind of just in the textbook. So I mean, if you really don't have time or cannot, I mean, because I scrolled up and down, if you cannot copy down the whole thing, that's okay. You can either read it later on or actually compare my notes later on with the textbook. As I said, I'm pretty much follow the proof of the textbook, but just kind of explain more. And I may write a little bit less than the textbook because the textbook proof is actually very long. Okay, so now let's see. So now I want to finally start defining the function we need. Okay, so once we have the set up the set here. So now I'm going to define the function, the global function, mi, okay? And I can really explicitly write down what the function is. Okay, let me copy down this thing. Okay, so now what's this, right? So let me give you, so essentially hi is from Rn to R, and it's smooth. And also hi is going to be positive in the coordinate ball that we have. Actually, not coordinate ball, sorry, in the open ball in Rn. And also hi equals 0 elsewhere. And you might wonder what hi is. Hi is essentially the bump function from, I think it's lemma 2.22, right? So that means everything is only exists inside this smaller open ball, and it's 0 elsewhere. So it's just a bump function, okay? And if you define like this, and vi is just the coordinate map, right? So basically, this tells you that basically, if you want to draw the picture, you have a original coordinate ball, right? And you have a slightly larger one contained in the, this is bi prime, right? And we know that we have a bigger open set in the open cover, right? And what you have with this fi is that it's going to be, so from the definition, you actually know that f is smooth. Because actually this is a smooth, hi is smooth, right? And vi itself is diffeomorphism, as we know. And actually, by this definition, we can see that the support of fi is actually in the closure. It's actually the closure of bi. So what does that mean is you actually have a kind of like a bump function inside bi, and everything else is 0. Okay. So this is the construction. My picture is a little bit bad, but roughly like this. Okay. So this is 1 here. And 0 outside the whole thing. Okay, so this is your Fi. Okay, so now let's see. So this Fi essentially gives us some bound function inside some coordinate ball. Okay, so now we want to add those things up. Okay, so this is essentially the trick here. So now we define a new function f. Okay, and the definition is just really add up those Fi. Okay. Okay, so first there's several features of this function f here. So first of all, because our definition of Fi is non-negative, right? Because we take the you take Hi compose Vi. Hi is between 0 and 1, so of course it's non-negative. And even more because the support is inside the ball, so coordinate ball. So actually in each coordinate ball, the Fi is strictly positive, right? It's only 0 when it touched the closure and then 0 elsewhere, okay? So this tells us that because of this, then because you add up all this sum here, right? And for each point X, it lies in some Bi, right? So you will always be able to find at least one Fi such that Fi of X is strictly positive. So basically this just tells you that then we know that for this F, it's going to be strictly positive on M, if you think about it, right? And even more, whenever we have this summation, we first need to ask ourselves, is this an infinite summation or like a finite summation, right? So, I mean, we will always worry about this convergent issue, right? But it turns out that if you remember what's Bi, right? Bi is actually, or you can say the closure of Bi, the same. It's locally finite. So this sum, right? Locally, you're only going to see finitely many non-zero terms, okay? Because Bi is locally finite, okay? So let me make a remark here that this sum here is good. So only has finitely many non-zero term in a neighborhood of each point. And the reason is because the closure of Bi is locally finite. That's where we use the lemma 1.13. Okay, which means that nearby at each point, right, in the neighborhood, you like when you deal with the summation, right, in the neighborhood of a point, it's always only finitely many non-zero terms. And you can see that actually we are getting closer to the definition of partition affinity, right? Remember, we want to have that kind of nice summation, right? But if you think about it, this summation is not 1 yet, right? It's not partition of unity yet, right? So we need to kind of twist the function a little bit so we can get 1 eventually, right? So now the trick is the following, okay? Oh, by the way, I forgot to say that this F is actually positive. And the reason, and then also you can see that this, first of all this Fi is smooth, right? And we are sum up maybe possibly infinite many Fi's, right? But if you think about it, as we just discussed, at nearby each point, you can imagine the sum is actually, I mean, when you take the derivative, you only worry about non-zero terms, right? So even though you are possibly adding up infinite many Fi's, but locally, the non-zero term only has finitely many. So when you take the derivative, you don't need to worry about having the convergent issue. So this essentially tells us that F is smooth, right? In M, okay. So that's actually give us the nice property here, right? If you just add up random infinite many function, then you need to worry about whether it's actually convergent or not before you can even decide whether it's smooth or not, right? So, okay, so that's one thing. So now we need to create the partition of unity, right? We need the unity here. So we now define some new function. We call it GI. And as you can imagine, to make it unity, you divide by the whole thing, right? Okay, so for each GI, it's just Fi divided by F. And since we know F is strictly positive, right? So we don't need to worry about the smoothness at each point. So this is also smooth, right? And because of this, just by the definition, we know each GI is between 0 and 1, right? Because actually, if you think about it, right, we want to add it up to be 1. And even better, you can just by the definition of GI, it's really add up to be 1 for each point. Right, because I divide by F, right? And the summation of Fi is F. So if I divide everything by F, the summation will be summation Fi divided by F, which is F over F, that's 1, right? But now you might wonder, okay, are we done, right? We have a nice function and the support is actually in the locally finite ball, and then the summation add up to be 1 for each point. It seems like we're done. We're almost there, quite not close, we're close, but not quite yet. So there's another issue we need to deal with at this point is that, remember what's partition of unity, you want it to be subordinate to each open set, right? And as I mentioned earlier in the definition, the family of function you create, right? Those per psi alpha, the index should match up with the original index for the open set, right? So in this case, we actually only deal with a subset of the index, right? So we need to kind of re-index our function or maybe throw in more in order to have the same family, right? So that's the last issue we need to deal with. Okay, just re-index everything and then we should be fine. So we want to re-index the functions. So they are indexed by the same family. Okay, so now the reason is, okay, so the way we do it is the following. So each a little bit larger coordinate ball is a refinement, right? Because that's the locally finite refinement of the open cover. Okay, so what's is a refinement. I'm actually writing down something completely different than what I thought, but okay, so it's a refinement of the open cover. Okay, so what's a refinement, right? Refinement means that for each open set in the refinement, it should contain in some of the original open set, right? So for each I, you have a corresponding larger set. So for each I, you have a corresponding index that's called it A of I, meaning this number A depends on I. And this is the index in A, right? Such that this Bi prime is going to be included in whatever the open set X something, right? So for example, if B1 prime is included in X alpha 1, right? Like included, right? So we have like a one-to-one correspondence for each I, right? So this is just a refinement. Okay, so then now we want to re-index. So for each index in the original family, now I finally can define a corresponding family of function. And it's a global function. Okay. So this function is actually very, very special. So we defined the summation of those GI. But for each alpha, you only add up the summation that when I would be the, so you only add up those i's such that bi prime is contained in the corresponding index. So you only add up I such that A of I, this index, is actually the same as alpha, right? So what does that mean? It means that, okay, for, let's say this is a particular, let's say x1, okay, that's called some name. And you might have, okay, this is B1 prime, B2 prime, and maybe B3 prime, right? And you have another, say, x2, right? And you have, I don't know, B4 prime, B5 prime, something like that, right? So for per side 1, right, that's corresponding to x1. Per side 1 will only be, you add up G1, G2, and G3, right? Because B1, B2, B3 prime are all included in x1, right? And you're not going to add up anything else. So that's essentially what the sum means, okay? So you do this kind of reindex, okay? Let me just, I kind of want to erase this so I can just write down everything, okay. Okay, so now we're almost there, right? So then you might wonder, is it possible that there might exist some alpha such that there's no corresponding I? It's possible, right? You might add, because it's a refinement, right? Because how do you know your open set X alpha might actually be too many of them? There are a lot of redundant, right? So you may not necessarily be able to find the corresponding BI. So we need to deal with if this case, if no index I such that the corresponding index is alpha, right? Then we take that particular family of function to be a constant 0. So that's why you can imagine, because the BI opens ball or coordinate ball you take is locally finite, meaning there might be a lot of them that's not that's 0, right? So that's why that's essentially how we reindex the family of function, right? So there will be a lot of 0, okay? Then in the end, by lemma of 1.13 and B, right? We want to make sure the support is also correct. Okay, let me just write this down. So the support of psi alpha, right? It's the union of those, the closure of union of those both where the index actually goes to alpha. And you can actually check it's the same as taking the union of the same thing. Okay, and each of them is going to contain in alpha, right? Because remember, we want the partition of unity to be subordinate in those open set. And we can actually check that each function psi alpha is small. And this is actually, just by the definition, you can actually check this is the case. Okay, so basically, from and then we can also check that the support is locally finite, because by the definition it's just all this set. Okay, so support is locally finite. And even more important, you want to add up this, right? So the function, if you add those things up, right, it's actually all the possible GI, right? And remember, back then we already know all the possible GI together, it's actually 1. Okay, so this is I'm doing a kind of like a rough scheme of how the construction is. As you can see, you need to do a very detailed construction if you want to do it start from the scratch. But this is doable, right? So basically, this tells us that if you give me any open cover, right, I can find a smaller like basis, like coordinate ball, right? And I'm going to build a bump function in each things. But I'm also going to build it very nicely that I'm going to reindex things or maybe divide some function such that I'm going to have a family of function that add up to be 1. And then later on, because I need to match with the index, so I'm going to call like re-index the family of function, right? And then there will be a lot of per psi alpha to be 0. So then it will guarantee that when you add up this function, it will still be 1. And then you also wanted the support to be locally finite. Okay. So as I said, the proof is actually quite involved. So I mean, I'm not going to test everyone like how to prove this, but I think the proof is worth understanding in the sense that then it actually used the bump function that we created before, right? And then how does bump function come from? It actually comes from, remember this spatial function we built, like it's 0 somewhere and goes up to 1, and then it's 1 after a certain place, right? So all this function, I guarantee you're going to see it especially if you later on do some research in analysis or PDE. People use this type of cut-off techniques or bump function all the time, especially when you're trying to patch two things together. Like you want to have glue something together, but you also want the thing to be 0 elsewhere. That's actually very useful. Okay, so we are going to see, so now we just accept the fact that for each open cover, we can actually find a smooth partition of unity subordinate to this open cover. So now we are going to see some applications. Okay, so the first application is essentially the existence of smooth bump functions. So back then, when I say bump function, what I mean, the h that we just saw is actually a bump function from Rn to R, right? Because you remember the domain of h is actually in Rn. But now, by using the partition of unity, we actually are able to build a smooth bump function on manifold, right? So basically, we just move Rn to manifold. And as you can see, because I mean, manifold locally is Rn, right? So we should be able to patch things together. So the statement is the following. Let's say you have a smooth manifold, right? Then for any closed set A, subset A, and if you pick any other open set U, which is larger than A, right? Then you can actually find a smooth bump function for A. But this bump function is going to be supported in U. So that means this function as a global function is going to be constant 1 in A, but it's in between 0 and 1 elsewhere, right? And then the support is actually in U, meaning it's 0 outside U. Okay, so if you look at the picture, it will be something like this, right? So you have some closed set A, right? Closed set, and you pick any random open set that's larger U, right? And you will be able to build a bump function, which is essentially 1 here, right? Up to heating. I mean, it should be higher dimension, right? And it should be 1 in all the points in A, but between 0 and 1. So this is something like this, right? And smoothen out. It's 0 outside U. Okay, so that's why we call it bump function. Okay, so actually the proof is quite easy if you admit that the partition of unity exists, right? So basically you just say, okay, I need some open cover, right? So I take the first open cover just to be U, right? It's an open set, okay? And I take the second open cover to be M deleting the 8, right? So the complement of A, right? This is open because A is closed, right? Then by what we just did, by the existence of partition of unity, right? We can have the construct essentially a smooth partition of unity. And because we only have 2 sets, so there's only 2 functions, right? Right, this 2 function, and it's actually subordinate to the open cover. Right, so you have 2 open set that give you an open cover of everything, right? Because you can see U0 union U1 is M, right? And then they will have some overlapping region, right? And so basically, let's say we only have two open sets as our open cover. I mean, we can definitely, by the existence, we can build a partition of unity subordinate to these two open sets. And because it's subordinate, then you can see that psi 0 is going to be 0 outside U0, right? And the other one will be 1. So we know psi 1 is going to be 0 on A, right? Because A is outside of U1, right? So this means then if you look at what's U0, right? U0, so for any point in A, then psi 0 of X is going to be, it's kind of dumb, but let's just do this, right? At this point, it's 0, right? Because psi 1 is 0 on A, right? But we know that because it's partition of unity, so it should add up to 1 for any point, right? And so this tells you basically that psi 0 is 1 for every point in A, right? So this is exactly what we want, right? This is the construction we need. And even more, the support of psi 0, right, is actually in U0. This is what we call the subordinate to this open set, right? And this is just U, right? So the support is also in U. So this psi 0 is exactly the function we are looking for this bump function. Okay, so this is essentially kind of just using partition of unity for two open set, and that's it, right? So you can see that we essentially patching things up to build this type of bump function, and by using the partition of unity. Okay, any question so far? So this is actually more involved, but like we're going to see partition of unity later on, like especially when we do integration, when we define some definition that only works locally, and we want to kind of somehow extend it to global, then we need partition of unity. Okay, so the remaining thing, I'm not going to prove too many things. I'm just going to tell you some application for partition of unity. But before we do that, I want to recall or actually define what does that mean to be smooth on possibly some closed set, from a closed set into some manifold. Remember, we actually defined this, right, on Hn, or some open set in Rn, right, or necessary closed set in Rn. But we haven't really make it rigorous on the manifold, right? So let's say if M and N are manifold with or without boundary, and you have a subset A, can be closed or open, right? Open is easy, but we want to include the definition for closed set. And I want to address that this is actually in a correction in textbook. So in the textbook, it actually only gives you one case, but I actually realized that the author actually posed the correction. So it actually modified the definition to be more rigorous. So it actually separates into two cases. Okay, so you have a function from any subset in M to N, right? And then the definition will be slightly a little bit different, right? There's a subtlety between the case when N is a manifold with boundary or not, okay? So the first case is when N does not have boundary, then everything is nice, okay? Because then N will behave like Rn. Then we say the map is smooth on A. This is what we saw before, similar. If for every point in this set, you can find a larger open neighborhood containing this point P. And also a smooth map defined on this larger open set, such that F delta will agree with F in the overlapping region. Okay, so this is actually exactly the same thing we saw when we're trying to make sense that, oh, if you have a open set in Hn and those open set might actually intersect the boundary. So how do you deal with the boundary point? Then this is the similar definition here. It's just now we are working with manifold. And the other case, a little bit subtle, is that when possibly the manifold N actually has boundary, then it's kind of similar, but you need to be careful. So the definition is the following. In this case, we said we still want to find an open set, right? WP in M, and also WP should contain in this point P. But this time, I want to find a smooth chart for N, such that the image f of P is in the domain V you pick, and you also want f of actually this should be WP intersecting A should be lies in content in this V, right? Then if you consider the function, right, this f will actually now be function from the domain to Rn, right? So you want this map as a map into Rn. Should be smooth in the sense of case one, because now Rn is a manifold without boundary, right? This is a manifold without boundary. So this is a little bit like they want to do like a very rigorous like definition here. So that's why we go through the a little bit like extra definition here. So this is the case two is not included in the textbook. It's actually in the author's like correction. So I actually want to include it here. Okay. So now keep this in mind. Then the next couple thing essentially is just the application for partition of unity. So with using partition of unity or bound function, right? We are going to have this. So first lemma 2.6 is what we call the extension lemma for smooth function. So that means, okay, if you have a manifold, right? And if you have possibly a closed set subset, okay? If this subset is closed and you have a function from A to some Euclidean space, which is smooth, right? So now if you have a closed domain, then the smoothness really means that if you have a point on the boundary, then you need to find a larger open set, right? Such that you have another smooth map, and which agree with the original one, right? So then you can do a extension, right? Then for any open set U containing A, right? You are able to find a smooth function globally f tilde, such that it agree with f in the original closed set A. And the support is actually in U. So what does that mean? It means, okay, I have a closed set A, right? And you already have a defined function f, right? Maybe like, I don't know, like whatever it looks like, right? It might be like, I don't know, like something like it, whatever, right? It's something like this, f. And you say, okay, I just find some bigger open set U, right? Then it tells me that I can actually find a smooth map globally, right? Your manifold might be larger M here, right? You can find a smooth map, I don't know, maybe like 0 outside, right? But inside you can do some patching, right? So it's 0 outside U because we want the support to be in it. But then it's going to agree with F inside the closed set A. Okay. So you can imagine that this is exactly can be done by some kind of like patching, right? You maybe multiplied by some Carnot function or like by some partition of unity, right? So essentially this lemma allowed us to smoothly extend my local smooth map on the closed set. Okay. Then the next question, the natural question you should think of is, what about open set, right? If I have an open set and I have a map to be smooth defining on this open set subset, can I always extend it, right? This lemma just show you if you have a closed subset and you have a smooth map defining on this closed subset, then you can smoothly extend it, okay? But for open set, unfortunately, it's a blessing, but it's also a curse in the sense that it's nice to work with smooth function on an open set. But at the same time, it also tells you that you may not always be able to smoothly extend the smooth function from an open set, from an open subset. Because the problem is that because it's open, right? Your domain is open, things might get bad when it near the boundary, right? Near the boundary. So for example, if you take the whole manifold to be R, real line, right? And you take your open set to be, say, from minus pi over 2 to pi over 2, then you can imagine the function you define, the smooth function tangent, right? It's going to be smooth in U, right? But you cannot extend it over the boundary points, right? Because you can see how your tangent is like this, right? From pi over 2 to pi over 2. There's no way you can make it smooth, but beyond pi over 2, right? Because you can see the derivative, actually the value is actually going to infinity, and the derivative is actually also going to infinity. So there's no way you can extend tangent function over pi over 2 and minus pi over 2, but at the same time keeping it to be smooth. So this is the unfortunate part, that you cannot just directly extend the smooth function from some open set. But what you can do is like back to use the corollary 2.8, where if you could find some like another open local smooth map defining an open set, and if they agree on where they overlap, you can kind of patch together, right? But other than that, I mean, you cannot just like directly smoothly extend a function like this if it's defining on an open set. Okay, so this is not included in the textbook, but I feel like this is a good comparison with the previous lemma. And the last application for partition of unity is the following. So we can define and find exhaustion function for any manifold or topological space. What's an exhaustion function? Exhaustion function is a continuous function from manifold or from the space to R, such that the image of this interval, closed interval from minus infinity to C, the preimage, the set of this preimage set, this is what we call the sublevel set, right? If it's if it's preimage of C, right, some value, then it's called level set, right? But since you're including the preimage of anything less than or equal to C, then that's why we call sublevel set. And the exhaustion function just means that if you have a continuous function such that for every such preimage, if it's compact, you want it to be compact, okay? So first, if you think about it, when does this is going to be true, right? If your original manifold is compact, right? So if M is compact, right? Then and F is continuous, then this is always true, right? Because what's this is a preimage of closed set, right? Then it's going to be closed in M, right? Because it's a preimage of closed set. But a closed set in closed subset in compact set, it's again compact, right? So closed subset in compact set is closed, is compact, right? So you can see that the exhaustion function, if you have a continuous function, right, and M is a compact manifold, then this will always be true. So you can imagine, like, if we want to work with exhaustion function or trying to find exhaustion function, most of the time we essentially want it to exist on non-compact manifold, right? If it's compact, then it's any continuous function will work, okay? So let's see. So first, I want to make this remark that if you have an exhaustion function, right? This is the note here. If F is a exhaustion function. So what's the good thing of finding exhaustion function? Then if you look at the preimage of this, I mean, maybe I should use N. right? If you take n to be any positive integer, right? Then it add this family of preimage, right? It's going to form what we call an exhaustion of M by compact set, right? So if you recall what's an exhaustion of M, meaning you have a whole bunch of compact set, right? Because you want to have an exhaustion of for compact set. So you want the exhaustion, the union together to be the whole manifold. But at the same time, each compact subset is included in the interior of the larger one, right? So it's like you have a kind of like a Russian doll, right? In the sense that you have smaller thing content in the bigger thing and in the bigger thing, and then all of them are compact, right? And then once you union everything together is the manifold. That's what we call the exhaustion of manifold by compact set, right? So essentially the whole purpose of having exhaustion function is that it will create an exhaustion for the manifold, okay? Especially when manifold is not compact, right? If it's compact, then itself, I mean, there's nothing to say, right? So I will give you an example of an exhaustion function from a non-compact manifold. Right, so you can think about this is going to be exhaustion function, right? So if you want to see why this is the case, right, then think about what's the sub-level set, right? If you find the preimage of each sub-level set, you can see that it's going to be the closed ball, right? Because everything when the norm is less than equal to some number C, right? So this is essentially a closed ball. So you have all the closed ball, right? And if you take larger and larger closed ball, it's going to union the whole Rn, right? But each of them is compact, right? A closed a closed ball is compact set, right? So you're going to create a nice exhaustion of Rn, right? And essentially, by using partition of unity, we can prove the following proposition that every smooth manifold, it's going to admit a smooth positive exhaustion function. Okay, so this is also can be done by partition of unity. So, but I'm not going to prove here. So the textbook actually mentioned a lot of application using partition of unity, but a lot of them, I think most of them, the author actually provide a nice proof. So if you want to read it, you can actually read it. But I'm not going to emphasize that too much because it's quite involved for some of them. Okay, so I think we probably need the exhaustion function or exhaustion like this later on. So that's why I just want to mention the definition. So in the next 7-8 minutes, I want to start the chapter 3 because I want to introduce the thing so you can actually start thinking about it or pre-read everything over the weekend. So chapter 3, the main point is to make sense or define the tangent space of an abstract manifold. When I say abstract manifold, means that I don't want to necessarily put this manifold into a bigger Rn, right? So for example, back then, when we think about the say the sphere, right, S2, and intuitively for each point you can have a tangent plane, right? That's the tangent space, and geometrically we can think of that. Oh, the tangent space looks like you have a plane, right? R2, like touch the point P, right? And then each tangent vector kind of looks like a vector starting from this point P, right? But if you think about it, this type of visualization may not necessarily be practical in the sense that then every time you talk about tangent space, then you need to put S2 inside R3, right? And then when you talk about the tangent vector you saw here, like each time you need to describe it, then you need to actually using the 3 coordinate, right? Because you kind of put it stuck in R3. That's actually a bad move because as an abstract manifold, you shouldn't need to do that, right? S2, as we already know, now we have a nice local coordinate, right? So we should be able to describe everything on S2, including the points or maybe the tangent vector by just using 2 coordinates, and that should be enough, right? We shouldn't always have to stock my manifold into something larger, right? Then it's actually redundant. It's actually not a good way to work with it. So we want to define tangent vector in a more abstract way that it actually serves our purpose, okay? But first, before we do that on general manifold, we take a look at Rn. Rn is the easiest case that we can think of, okay? And there are several ways, actually, if you read the literature, either our textbook or other textbook, you will see that different people have different treatment of how to define the tangent vector or tangent space. But eventually, they're all the same. You can always identify or make one definition equivalent to the other, okay? So the first, let's start with what the textbook called the geometric tangent space to Rn at some point A. And keep in mind, we should separate the tangent space or at A, point A, with tangent space at different point, right? So you should think of it as an independent space, right? For example, you look at the sphere, right? The tangent space at P looks like a R2, like a plane, right? But you should not you should not like if you pick another different point, right? You will have a different tangent plane. You should separate those 2 tangent plane, right? Even though the vector might look the same, okay? So you should separate it. So for each point A, we define a geometric tangent space. At this point, we use this notation, R to the n sub A, meaning it's the tangent space at A, okay? And you can imagine it's going to look like, everything looks like the point A, but paired with the vector, right? So if you think of S2, then it's like point P, and you pick a vector, right? Tangent vector on it, right? And the tangent vector is any vector that can be in Rn, right? So basically, this will be the definition for what we call the geometric tangent space. And each tangent vector, right? So each, you can think of a vector B with initial point at A, right? So a bad, maybe not so correct, but like a rough geometric picture can be like, so in Rn, right, in R2, you have a point A, as if you attach a R2 plane to A, right? And your vector V will looks like some vector starting from A, right? And each element, right, each element or vector here, I use the notation vector V, but I do this kind of thing. So the text would do a sub A. This just means that you have a vector, tangent vector at the point A, right? Because as I said, you should separate tangent vector at A with tangent vector at B, right? They're disjoint union. The tangent space should be a disjoint union. So we should think of R and the collection of all the tangent vector, right? The tangent space are disjoint if the point are not the same. Right, we should separate the tangent space. Okay, and we also have this nice operation. If you add up 2 tangent vector, right, then it will looks like as if you consider the addition of the vector, but you restrict at the point, right? If you think about it, this should be true, right? If you're talking about a vector, say, I don't know, 1, 2, right? At a certain point, that's your tangent vector, and you have another vector 2, 3 at point A. You can add them up, right? And also we have this scalar multiplication, right? So if you take C times a tangent vector at A, this is as if you take the same vector multiplied by C, but you restrict it on the tangent space at A. Okay, so the last thing I just want to say is that it turns out that this is not necessarily the best way to do it. This is more geometric, right? You think of it in a picture, you have a vector, but then this works well in Rn, but not necessarily works well in general manifold. Okay, so the point is that now I want to identify. We can, and we actually want to identify a tangent vector in this sense with an operator or a map in some sense. With I want to be vague at this point with certain property. So the best way to think of this is that, okay, now if you give, let's say you fix the point, okay, let's say everything is at A, okay, you take a tangent vector at A. Instead of thinking of it as a vector, we actually can identify or find a corresponding linear map that's essentially corresponding to this vector. What's the perfect example, or actually the example here is that thinking about taking directional derivative, right? If you give me a vector V, and I can view V as an operator or map, right? What's this map looks like? You input a function. I output the directional derivative in the direction given by this vector V, restricted at A, right? So as if you're taking the directional derivative at A in the direction V, right? So for each vector you give me, each vector V you give me, I can have a corresponding directional derivative at point A. And you can see now this is a one-to-one correspondence. That's how we identify a vector with some kind of linear, you can call it linear operator or linear map. And later on, we're going to see that this type of definition is what we are going to use to abstractly define a tangent vector on the manifold. So basically, later on, we're going to see for map like this, for example, directional derivative is one of them, has some nice property, okay? So we call all this map satisfying this property, we call it derivation. And then we are going to define a tangent space on the manifold to be the set of all possible derivation maps. Okay, so this is more abstract, but you're going to see that it has similarity with what we saw before when we view vector as a tangent vector of some curve on the surface. Okay, so this has a, if you restrict it to the surface or specific case, it actually match with what we saw before in curve and surface class. Okay, so I want to start the tangent space like this, just to give you a heads up so you can start reading it over the weekend. It start getting more computational in some sense. And then sometimes the notation, you need to kind of get used to it. So I would really highly recommend that if you have time, of course, like start reading some of them so you don't find the notation to be too overwhelmed. Okay, so so I'm going to post the homework part 2 tomorrow, sometime tomorrow. And if you have any question, feel free to ask me, or actually feel free to go. Have a nice weekend. Thank you.